Hi everyone, and welcome to another video of this channel. So in this video, we will investigate problems 20 through 22 from the 2012 AMC 10A. So I haven't been able to post any new material lately because I was prepping for the AMC 10 myself. But now we can start the channel up again with some new AMC 10 problems. So let's dive right in. We have a 3x3 squares that is divided into 9 unit squares, just like this. So, kind of like a Sudoku puzzle. And then each unit square is painted either white or black with equal probability. And then the square is rotated 90 degrees clockwise about its center. So how would that look like? Well, if this square right here was black, then it would rotate like this, and the black would end up in this square. If the square was white, like in the corner, it will rotate to the corner on the right or on the top and would become white. And then the center just stays where it is. But there's a catch. What if this square right here is white? It rotates to this square right here. Now, before we rotated, this square was occupied by a black color. And so, this white square will land on the square formerly occupied by a black square. And this white actually gets cancelled out. This square remains black. And so we have to find out what is the probability that the grid is now entirely black. So probability means favorable outcomes over total outcomes. So here is the chart or like a larger version of the Sudoku puzzle we will be looking at in order to solve this problem and to analyze it. But before we do that, the total outcomes for the initial colorings, there are 2 ways to color each square, right? Either white or black, and there are 9 squares, so 512 total outcomes. That's why a lot of the denominators are powers of 2. So now we will do a bit of casework on first the center, then these side squares, and then the corner squares. So firstly, can the center square be initially colored white? Well, no, because if it was initially colored white, the center square would rotate on itself and remain white. So this actually can't happen. The center square has to be black. For our favorable outcomes, that is 1 total coloring for the center. And now we'll split up the remaining 8 squares into the 2 groups of 4, side squares and corner squares. So let's suppose that we have no white squares on the side. So right now we're going to do casework on how many side squares are white. We're not going to worry about the corner squares at all. So we can have all black squares, right? If we rotate them clockwise, all the side squares will remain black. So we have one possibility right there. But what if one of them is white? Well, that also works. No matter where the white square is on this group of side squares, when it rotates to fill this black position, since this square was black before the rotation, it remains black after the rotation. So this white square can actually be anywhere in any of the side squares, and there are 4 side squares, so that's 4 other outcomes. So now let's focus. What if there are 2 white squares? Can they be next to each other? And the answer is no, because this white square will rotate onto this white square, and this square will remain white. We want all of the squares to be black. So this actually can't happen. If we have 2 white squares, they have to be opposite each other, and then the other 2 squares will be black, just like this. And this is actually a proper combination. So this white square will go here, this square remains black, and the same thing is true here. And so we have 2 places where we can order the white squares, right? Either here and here or here and here. And that contributes our final case. So why do I say final? Because if we have 3 whites, then this square and this square will remain white after the rotation. And of course, we can't have all white squares. We have 7 total possibilities, 7 total colorings of the side squares, such that when we rotate, all of the side squares after the rotation will be black. Now, what about the corner squares? Well, we can notice a bit of nice symmetry in here. Um, just because the corner squares are spaced differently and positioned differently in the plane as the side squares, that doesn't mean that their rotation will change, right? Because they are parallel to each other or like perpendicular to each other, equally distant from the center, and so on. So there's actually perfect symmetry. And the total number for the corner squares is also 7. And so, in fact, there are 49 total ways we can color this board right here so that after the rotation, all of the squares will be black. So 49 favorable outcomes, and the total outcomes is 512. The answer is 49 512ths probability that the square will be entirely black after the rotation. So now here's problem 22. This is definitely the highlight of this video. So the sum of the first m positive integers, so that can be written as 1 plus 3 plus 5 all the way to plus 2m minus 1, where there are m terms in the sequence, is 212 more than the sum of the first n positive even integers. So this time we're summing even integers, and that can be written just like this, given that there are n even integers. What is the sum of all possible values of n? So we are trying to isolate n and kind of work within this. So dealing with these summations is, a bit complicated. So our goal is to find kind of a closed formula for these sums. And if you got this far into the test, you probably know that the sum of the first x positive odd numbers is x squared. But I'm going to do a quick geometrical proof here. So first we draw one dot, right? That represents the 1. Then we add to it 3 more dots. That represents the 3. We can divide the 1 dot from the 3 just to outline that they were from separate terms. Then we divide the 3 dots off and draw 5 dots. And that's the next term in the odd sequence. And so notice that the result is a square. It has side length x, where there are x odd numbers being summed, and its area, so the number of points in it, is just x squared. But it's also equal to this thing right here. So that is the proof of this formula right here. So this is in fact m squared. And then the sum of the first x even integers is x squared plus x. And we can notice that we can write 2 as 1 plus 1, 4 as 3 plus 1, and so on. And then we can write 2x as 2x minus 1 plus 1. And so we highlight all of the resulting odd terms. Notice that their sum is equal to x squared. And then there are x1s left over, right? 1 for each term in the sum. So it's x squared plus x. And so, in fact, we can really compress this equation into m squared equals 212 plus n squared plus n. And once again, if you are doing this problem on the test, you probably know these formulas. So, since we want n, right, we write a quadratic in n, just like this, and we use our quadratic formula. So we have n is equal to -1, plus we don't use the minus because n is positive, just like this, minus 4ac, and then over 2. We can simplify this a bit and make a substitution. So this is like a really common use of a substitution in these types of problems. So we can substitute all of this with p squared. So 4m squared minus 847 equals p squared, which means that this big radical right here is equal to p. So this implies n equals -1 plus p over 2. So if we can find all the possible values of p, we can find all the possible values of n and then add them. So first we rearrange our equation like this, and the right-hand side is nicely factored in a difference of 2 squares. And now, obviously, these two are integers. These two have to correspond with some integer factors of 847. And the factorization of 847 is, in fact, 7 times 11 squared. So its factors are this right here. So 847 times 1, 121 times 7, and 77 times 11. Those are its factor pairs. Now notice that 2m plus p is obviously greater than 2m minus p, so 2m plus p corresponds to either 847, 121, or 77. And so we can set up 3 systems of equations. So either 2m plus p equals 847 and 2m minus p equals 1. And if we solve that, we get this right here. So m equals 212, then p equals 423 just by plugging in, and then n equals negative 1 plus p over 2, which is equal to 211. So that's one of our possible values of n. Now our second system is 2m plus p equals 121 right here, and 2m minus p equals 7. And so m equals 32, p equals 57, and n equals 57 minus 1 over 2 is 28. And finally, our last system right here, just like this. So m equals 22 from this system, p equals 33, and n equals 33 minus 1 over 2 equals 16. So these are the possible values of n. We don't have any more systems because 2m plus p has to be greater than 2 minus p. If we go further, that won't be true. And so we can just add them up, and we get 255 as the answer. And so that is answer choice A. I hope you liked this video. Thanks for watching. Don't forget to subscribe to this channel, and thank you very much.